thank you very much. Very much feel honored to be introduced here in this way. Yeah, that's true. In fact, I'm engineer, so it will at a later stage become a little bit mathematical. I try to keep it fundamental, but we'll see. Probably time to ask questions at a later stage. Well, NASA started recently a new initiative for advanced statistical turbulence modeling. The reasons are manifold. I mean, the disagreement would be among the state-of-the-art CFD tools, computational fluid dynamic tools, with respect to prediction of drag, so when you design an airplane, and the location of extended separations, so complex flows, say behind a commercial airliner. That is one serious problem. Existing turbulence models cannot accurately predict circulation control. That means the lift of an airplane. In particular, if we have high jet blowing conditions, and if you look at, and I'm an engineer at university and I have learned airplane engineer, the number of aerodynamic design cycles for designing new airplanes is stagnating for about a decade or maybe even more, despite the fact that computational power is still increasing according to Moore's law. And here, Krivers Moore, which is for hardness. So we have this enormous increase of computer power. Still, we are not in a position to say make fluid dynamic prediction such that an airplane, so to say, could be built according to that design. That simply doesn't work, and that is rather different compared to solid mechanics. Of course, we do experiment in solid mechanics, but usually the design process in solid mechanics can be done in a computer without extensive involvement of experiment. That is very different from fluid mechanics, very different. So, turbulence models, and we see that later, are the bottleneck for flow prediction. That is one main problem that hinders us to, so to say, make a major advance. Well, this is in line with the common notion I very often hear. We need more physics in statistical turbulence models. There's too much empirical behavior in the models. We need that. So the key question is, what is new? What is more physics? How can we put more physics in models, in equations? And how do we include this in models? So this is two key questions. And what I will try to convince you, that the answer lies in what we call least symmetries. Sounds strange, but I will teach you later what that means and what is behind that. Let's first look in the history of symmetries. So when I talk about symmetries, I mean these symmetries, and I'll explain to you in a minute what this is about. The special relativity, Albert Einstein in 1905 paper contemplated that the symmetry principle is the key feature of physics. So he was the first one to recognize it. In the 1920s, in quantum mechanics, symmetries have been established, so to say, as the axiomatic basic properties of quantum mechanics at the time. And today, symmetries are the foremost guiding principle to understand and model new physical laws today. You have to establish certain symmetries, and then the physicists try to derive certain laws. Hence, for statistical turbulence models, it's most natural to say symmetries of the fundamental equation of turbulence are to discover and used for our understanding. That's what I will talk about today. And of course, and we just started doing that, engineering turbulence models should be developed with symmetries as the guiding principle. So that is, so to say, the main idea I would like to transport to you today, so that we can use it. So what I will talk about today, that is essentially what is a symmetry, what is symmetry breaking, all that you may have heard in some journals, what is invariance, and then of course we believe that Navier-Stokes equation in particular are the best model we have to understand fluid flow, in particular turbulence, and there is good reason for this to believe. And then it becomes a little bit more involved here. I will go to this multi-point, I will talk about some statistical symmetries, and then I will show you a couple of results, and then I will sum up and give you a conclusion. Well, let me first explain what is the concept of a symmetry. I mean, when we talk of an object, of an everyday object, say this is a symmetric object here, why do we think it's a symmetric object? Because when we rotate it, it looks the same. So we add, so to say, we impose an operation on the object, on the geometrical object here, maybe the cylinder, but the object itself stays the same. That is what we think a symmetry is in our everyday life. The mathematician Sophus Lie, and that is the reason why they're called Lie groups or Lie symmetries. In fact, he is not from Asia, he's Norwegian. Lie is a typical Norwegian name. He introduced this idea of symmetries together with some other, also the German mathematician Felix Klein, and he said, well, we can find something similar in equations, right? I mean, physics in particular rely on equations. So if you have, and most usually we have differential equations, so Navier-Stokes equation, and then we have all kinds of other equations, Maxwell equation in physics, and many other, the Einstein equations. So we have a differential equation where this is the independent variable, this is the dependent variable. Now what we do is we introduce a transformation. Simple transformation, I'll show you in a minute an example. So we introduce new variables, new independent variables, and then if we put that into the equation, we want this transformation be as such that the equation looks the same. So they have, if you look at the equation, they look the same. Just compare terms, and they're simply the same. So that means written, of course, here in star errors. At the same time, and then you see that in a minute, the symmetry maps the solution. So suppose we have a solution also to another solution, but maybe. So this is a simple example. Those who studied physics, mathematics, engineering, they have seen this equation before. This is the heat equation. It's simply an equation that describes the propagation of heat in the rod. So if we have a long rod, and we put in heat here, it propagates in the of it's spreading up. This is the heat equation, here the simplest version in 1D. So a symmetry transformation, and that is what I said before. Now let's introduce this transformation. So we go to a new set of variables, x star, t star, and this capital T, which is the temperature itself, and we rescale this. So we rescale the independent variable, the spatial variable, the time, and also the temperature. So if we take that, and remember the chain rule of transformation, and we go into the heat equation, we see it looks the same. So this term is the same like this one, so it can be taken out. So this equation looks the same, and this was but just written here in the star variables. So this looks like a game, and at the first place it's not quite clear why this is so important. And in fact, as I said before, this is the most fundamental principle probably we know in physics, and so to say is in any of the physical models we have, that is quantum mechanics, that is relativity, that is classical mechanics, and other things like string theory. So this behavior, not necessarily this one because it's a heat equation, but the behavior of symmetries is extremely fundamental. So now let me define something more. So remember, we have the symmetry, so that maps an equation to itself, but at the same time, we can define something that does not change under this transformation. And I did some guessing, you can compute this. So I introduced this quantity gamma and delta here, and let's say x over square root of t, that is an invariant because, let's suppose we introduce that here for the x, and we have e to the minus ax star, so we just resolve it here, and here we do the same thing for the time here, and you can see you have the square root here, that cancels, so this thing looks the same, so we call this an invariant. So this quantity, gamma and also delta, do not change, they do not change under this type of transformation. And this is, well, again, it looks like a game, but it has a very important consequence. If we now go and say, well, let's take the gamma and the delta to be new independent and dependent variables of the system. So we say gamma now, the delta here is our new dependent variables, and it only depends on the gamma. Now we do this, so we take that, put it back in the heat equation, we find something very strange. We find that the heat equation reduces to an ODE. So this equation only has one independent variable, that is the gamma heat. And that means we have, so to say, a special solution to the heat equation. For this we can relatively easily solve. It's an ODE, it's linear, and it's no problem. So we kind of, with this machinery, we generated a solution of the heat equation. One solution, not the most general one. So that is the second thing that is important. One last thing what is important is, I did not think about boundary conditions. So suppose this rod is just here fixed to the wall, and the wall has a given temperature. So say the temperature at the wall is T0. And it stays here. For some reason we can manage that this is T0, and then this is a boundary condition. So that means at this origin here, the temperature should be given temperature maybe 5 Kelvin. Now let's ask the question, what happens if we look at the symmetries and implement the symmetries into the boundary conditions? So far we only looked at equations, but of course engineering problems are determined by boundary conditions, by the shape of the geometry, shape of the airplane. So the point is, if we introduce this boundary in the symmetry in the boundary condition, we can see the following. The A1, we can just simply take that out here. So you multiply by e to the A1, it goes out, but here you can't. So the A2 has to be 0 in order for the boundary condition to look the same like this. So this has to be 0, this can be arbitrary, and then we have the same form x star equals 0, t star equals t naught. So that means we lose one parameter here, that is the A2 is 0, while the A1 is remaining 1. And it's, so the T0 is symmetry breaking. So we impose something on the system and we lose a system. Well, now let's go to what we probably also saw in Wolfgang Schroeder's talk. We do believe, and there's good reason for that, that this equation here determines flow around, say, an airfoil or an airplane and all kind of other things. And further, some of you may not know, there's the Navier-Stokes equation here. It became one of the 7 millennium problems of mathematics. And as you know, the famous Mathematics Institute in the US gave out $1 million who can solve some of the main questions of this equation. Most important maybe here for this country, the mathematician Gregory Perelman recently maybe about 10 years ago, solved one of the 7 millennium problems, the famous quantum problem.
Should I shortly comment on that?
Sure.
He says, what is worth $1 million if I can have a universe? He rejected the field method.
He rejected the field method, he rejected the price from the institute, he rejected the $1 million, and unfortunately he stepped out of science, at least at what we know today. That is a pity, but just reading a book about him is very interesting. So, one of the 7 millennium problems, I'm not sure if that will help us engineers to design airplanes, if that will be solved, but it will give us some very deep information. So, what do we know about symmetries of Euler-Navier-Stokes equation? And I have to say, these symmetries we see here were, at the first place, all discovered here in Russia. Symmetries were very, very deeply studied here in Russia, in particular in the school of Osanistov, which some of the people may have heard, and that, so to say, is still exploring the area of symmetries. And there's a strong school here in Russia. So what do we learn? So suppose, remember we had the scaling of space in the heat equation. We have now the spatial variable time here. This is the velocity, and this is the pressure. So we rescale the velocity and the length scale. At the same time, but independent of that, we can rescale time, and we can rescale also the velocity. Of course, velocity is length over time, so this is, so to say, in the denominator. What else do we know? We do know what is Galilean invariance, so to say. This is the heart of classical mechanics. Suppose you move in a constantly moving frame here, that it means if the F here is B times T, B is a constant, that means whether you do an experiment, if the whole thing is not moving or you're in a constantly moving frame, that is classical mechanics, and any model in classical mechanics, of course also Turbin's model, should be consistent with that, which is not true for all models. In fact, I actually got some papers to review where this is not the case, but then you're completely out of classical mechanics and you're probably out of physics in general. Further, if the F here is a constant, that means simply that here you can shift your experiment, that is a constant, then, oh no, this is 0 and this is 0. It just simply means whether you do your experiment here, or you do it there, that should not depend on the coordinate system. Of course, that should be part of physics. So in particular, this type of symmetry here is part of any physical, fundamental physical law, whether it's quantum mechanics or relativity or even classical. There's a couple of more symmetries in the Navier-Stokes and the Euler equation. I'm not talking about that, just give you a flavor here. All these symmetries, of course, should be also in statistical equation. Turbulence is a statistical process, so to say, and the question is, can all this knowledge here, which is the heart of mechanics, can we transfer that into turbulence models? And the answer is yes, we can do that. And essentially all the modern turbulence models are consistent with that. I'll come back to that later. So that's fine, which was not true in the early times. People developed models which essentially were out of mechanics in a sense. So they were essentially one-problem models, so they were not uniquely applicable. Now let's go to turbulence. In turbulence, if some of you have heard some turbulence course, what we do is we say we have a mean quantity, so a mean velocity, and around this mean velocity is a fluctuation. That is what we see, what we believe is, so to say, the heart of turbulence. And then if you use this here in context of the Navier-Stokes equation, here the continuity is no problem, so to say, the continuity of the mean value, mass conservation of the mean value is the same as for the instantaneous. But for the Navier-Stokes equation, so this part here looks the same, but we have this ugly closure problem of turbulence. That means we have an extra term here, that is what we call the Reynolds stress tensor, and that so far had to be modeled empirically. That is one of the key problems, and that is the reason why we have so many problems designing airplanes using this type of equation, and there's good reasons that we have to use it, but we somehow have to, at some point, impose empirical laws to make this a closed set of equations. That is one of the reasons. So, for example, as an airplane designer, you get from your boss or from the company a large CFD code, and then usually if you go to the code and you have to choose a turbulence model, that means there is dozens of models on the market for this particular term, and if you go into the fall down menu on one of the models and you compute your airfoil or your airplane, you get always different results. That is what I just mentioned earlier. So every model gives you a different result. And that is of course not acceptable, and that is mainly the reason why we are not able to handle turbulence in particular on a more better fundamental basis. So just one more time here, this is what we call the instantaneous values. That means the velocity, so to say, we measure at some point. This is the mean value, so to say, the average, say, over a long time. And people do exactly this. They start the wind tunnel, put in a measuring device in there, and then the average over a long time, and then they have the mean value. That is what usually engineers and physicists are interested in, and that will be used to design airplanes. Further here, the little u and the little p, the lowercase letters here are the fluctuation values, so of course turbulence means there is fluctuations in it. In the turbulence theory, people developed something they called the two-point correlation principle. So what you simply have to do is you take the mean velocity, the velocity at one point and here at another point, so x plus r. So there's a difference between the 2 points, and you measure the velocities at these 2 points, and you average again in time. So that you can define. That has good reasons for doing that. I'll explain that in a minute. And you can do the same thing for the fluctuations. That is the classical approach. You can do that for the fluctuations. And once you have, so to say, this 2-point tensor, if you take the r equals 0, you essentially get what we had earlier. That is exactly what we have. So suppose we have, so to say, this 2-point tensor, we can compute this Reynolds stress tensor. Still, that doesn't solve the problem in general, but how can we solve it? This topic looks very ugly, I'm sorry for that. You don't need to look at all the details, but what you can do is, you can define something, not only measuring 2 velocity at 2 points, you can do that in more and more points. So you get a much richer picture of turbulence. It means you get, so to say, spatial structure information how turbulence is. Now you take the Navier-Stokes equation and you can write down an equation for that. For those who are a little bit familiar with the equation, it looks a little bit ugly, but not too bad. I come to an equation that looks much worse. Yeah, and the reason that, because it looks so worse, we don't use it, because we use this one here. Well, what do we see in this equation? This h here is, so to say, the tensor of this multi-point correlation. Now look at this index here, so this n plus 1. The bad news is the turbulence, the closure problem always, so to say, rises in half, so to say, in every equation, no matter what n we have, because you need information for the tensor that is 1 order higher. So that means if you write that down, so to say, for every tensor, you have an infinite set of equations. That is something that is known to turbulent people. Turbulent statistic, and to describe turbulent statistics, so to say, is very ugly. You need to solve infinite many equations, and it's quite obvious you can't do that on a computer. A computer can only swallow a finite number of equations and solve them. Cannot deal with infinite number of equations. But we can do analytically. So we can learn something. We can learn something from this type of equation. And then, well, one more thing is important. Those who may have an engineering, mathematical, or physical background, this equation here is linear. And this is nice. Linear means you can do superposition principles, say. And you can, there's all kinds of other machineries you can use to solve the equation. So linear is nice. Now I come to the really ugly equation, and that is this one here. This equation here is for this RHA. If you look in a book, in a textbook of turbulence, you will more likely find this equation than this one. But this equation is nonlinear. You can see that there's one term here multiplied by the gradient of some other things here. So there's a bunch of nonlinear terms. And in particular, all these different correlations, they're all coupled. So the whole system is nonlinear, terribly coupled. So we don't like to use this approach here, but we use like this approach here, which you essentially probably don't find in any textbook, which is surprisingly. And but this equation we can analyze. We can try to understand what are the fundamentals of this equation. Now, of course, using the symmetries. There is nonlinear behavior, I skipped that. Now let's come to the idea of symmetries in the statistics of turbulence rather than in Navier-Stokes. Remember I mentioned that in Navier-Stokes we have this translation invariance, whether we do experiment here or there, or whether we have Galilean invariance and there's other things. This is all in here. You can show it. So all the physics from Navier-Stokes equation is in here. So all the symmetries are here. But what we can do is you can investigate this type of an equation, and surprisingly, you find more symmetries. And we found that way more than 10 years ago, and I could not make sense of it. I was thinking, well, why could an equation that comes from Navier-Stokes that describes fluid turbulence, why should it have more symmetries and, in a sense, more physics than original Navier-Stokes? And we always put that aside. We said, well, maybe we mention it, but we cannot make sense of it. And then a couple of years ago, I made a 180 U-turn, recognizing this is the heart of turbulence. You need to understand these symmetries we find in this equation, this multi-point equation that describes the full statistics of turbulence, and we should try to make sense of it. And it works. It works very nicely, actually. And I will show you, for those who are a little bit familiar with some mathematics, you can simply guess some of the symmetries. So this is the derivative, here's the derivative. So all the terms are under a derivative. And that means to any of the terms, we can just add a constant that will go out. Similar to, remember, the heat equation. We find a transformation, we transform here to the Stark quantities, we introduce a transformation in the equation, looks the same. And this is one of the most trivial symmetries you can think of. So just add something here, and if you write down the equation in this Stark quantities, go out. This is going to say this goes up. We later recognized these type of symmetries, which looks very strange in the first place. They are the key ingredients, and those who work ever with turbulence, they are the key ingredient of the log law. It's a very famous law that was developed by the Hungarian engineer and physicist von Karman and the German engineer Prandtl. You find the log law in any textbook, but you don't find anything of this sort here, and understanding where does it come from. That's been found in numerous experiments, whether you measure on an airplane, whether you do an experiment in the wind tunnel, even the atmospheric boundary layer. It's so to say you have a long pile and you measure the velocities in the atmospheric boundary layer, say the first 50 or 100 meter, you do find this log law. But there was no first principle derivation, there was no understanding and understanding what kind of solution is this. Usually it was, so to say, it's more dimension analysis, but now we understand the log law, which is very old, is, so to say, a part of the solution of this type of equation, and we need these additional symmetries which we found in this equation. So there's one more. I maybe skip that one here. So you find more. Now we look at some examples here. Some canonical flows. So we say this is not an airplane, and we are not that far already to say we can design an airplane with this idea, because we still have the problem with this infinite number of equations, but that is at some point that's solvable. So we look at certain flows, so we call this canonical flows. They're not really technical, but they're close to technical. Engineers and physicists always, sometimes also think about even simpler problems like isotropic turbulence. That means you have infinite space turbulence. We go more closer to engineering problems, and for this type of problems, we can do something very nice. We can ask the computer to solve Navier-Stokes equation, so to say, numerically, and then from the solution of the Navier-Stokes, we can compute statistics. And right now we're running on one of the big machines in Munich, and some of you have ever done maybe CFD. We are right now in the position to compute one of these cases here, a similar case, with 10 to the 11 grid points. That means this run of the solution of Navier-Stokes equation sits in this supercomputer for a couple of months to get to, say, statistics on it. But with the Lie group, we are able, in fact, to describe several of the regions which are important of this type of flows, and I will show that to you in a minute. This is a very classical case here in turbulence theory and turbulence. So simply a pressure-driven flow. This is two plates. Velocity here at the plates are 0. This is a boundary layer flow. That means, so to say, there's a plate, but up there, so to say, we have infinite space. That comes closer to an airplane, say, where an airplane goes through so now of course up and below, of course, there's infinite space. Very often, many technical applications have rotation. So if you start rotating things like the turbines. Of course, the Earth is rotating, and we have to take account special forces, say, for weather forecasting. So this is a special case. And also, in some applications, we have something what is called transpiration. So we have a porous wall. So you say you're pumping air from below and you suck it from it. So these are canonical cases, not really technical, but so to say close to technical. And now what we're doing is we're putting all this symmetry stuff together and trying to find a solution to this equation for some of these problems. So this is the condition here. Remember here, that was the mean velocity. That is, so to say, the distance from the wall here, the nstu. So what we see here is some kind of a little bit funny differential equation, but we can solve that one here. That is simple to solve. And once you have solved that in fact, that gives you a solution to this. That is a nice part. So let's go to the famous log law. And if you look at some textbook in turbulence, you will hardly find any textbook in turbulence where this formula is not in here. But right now we have an understanding. This behavior here, the mean velocity is u bar here, this is valid in the region very close to a wall. And you can imagine, if you think of an airplane, the turbulent motion very close to the wall of the airplane, of the wings, of the body, that is, so to say, the heart we need to understand. So this law here is valid in this region here, very close to the solid wall. And what we can do is, we can sort of say, from this equation here, if we go back, just take this one here, rewrite that a little bit, we come to an equation that we can easily solve, and we can actually show that the log only comes if these constants are zero. And now if you remember, and what I told you earlier, if this here is zero, and we look at this type of symmetry, this constant here, this quantity here, that should be zero. That means this quantity here, e to the zero, is 1. That means this one here cannot be restated anymore. That means at the same time we have something symmetric. Von Karman derived this here, and they were very smart, they were extremely smart, understanding that this u tau here, what we have looked on turbulence, that is a certain velocity related to the drag of the flow, that this is the key quantity. So he formulated everything based on the u tau, and now today we understand the u tau is the quantity that what we call symmetry breaking. That means we cannot rescale this here, that means this whole quantity here is 1, or in other words, this sum here has to be 0 because e to the 0 is 0. So, what we understand now is we can derive even some of these very classical laws from first principles. That means we just use the symmetries, which are very fundamental to any part of physics, and we can use that and derive something that you find in any textbook, but if you look at the derivation here, you will never find any solution of any equation, in a sense, and that comes from the original equation. Further, we'll not go into details here, you can derive also things, remember what we had earlier, this is this Reynolds stress tensor. This is the thing, what is unclosed in the Navier-Stokes equation. So you can even write down laws for these tensors here. You can compare them. You can compare that to certain results. This is a DNS here, so that means a large-scale computation of Navier-Stokes on a supercomputer in Spain. So we do see if that is, so to say, the velocity, that is the distance from the wall, and if you write that here in semi-log version, most of the people who do turbulence know that, and you see if the log is true, you see a straight line. So log is true if you have linear scaling here, logarithmic scaling here, and at the same time, in this region here, we can also predict the stresses. So that is what we usually after when we do modeling of turbulence, that we can predict, so to say, the shape of the stresses. This one here, we can do more. Remember this case here, 2 plates, pressure gradient comes through air, highly turbulent here. Again, you can use this equation here. You need to introduce other constraints, symmetry breaking constraints, and you get something look like a power law. So you have x2 to the power of something called power law or algebraic behavior. And interesting enough, this number is very close to 2. You don't know why, but this mystery of these numbers will come later. If you look at data, and that is one of the best plots we have, now in order to see in data whether this is true, you do the following. You do a double log. If you do a double log scaling and you plot the data in this double log scaling, so the solid line here, solid line is the theory, while the dots here, there are more dots here, and the closer to the wall region. So you see in the core region, it's almost perfectly in algebraic. You can even continue with that, so you can even find the stresses, all that what is unknown in the Navier-Stokes, what engineers will need. So you can write down that. You can even see here in the core region, we can describe all the stresses, this is U11, U22, and so on. So you can describe all that very, very nicely with this, symmetry-based ideas. You can now do other things. Let's suppose we do this channel flow here in a rotating frame, and people actually did experiment on that. They have really a large roundabout. They put all the experiment on this roundabout and they start rotating. So similar to what we have on the Earth, right? I mean, there's what we call Coriolis forces. Again, you can crank the machinery, and those who are a little bit closer to physics here, the rotation rate we call omega 3 here. Of course, omega is 1 over a time scale, and that means a time scale means we impose, to say, an external constraint which is symmetry breaking, and that at this point the scaling of time is not possible anymore. Put that in the equation, and then at the very end you find a very simple linear law. And the surprising thing is all this, there is some older DNS, but also experiments, that is not up here. We do find that in the center region of the flow, a highly turbulent flow, you all of a sudden see that the linear behavior appears, which at the first place is surprising when I first saw that. I couldn't hardly believe that, but it's true. The DNS showed that, the experiment showed that, and also we have a machinery to understand that from theoretical. Maybe I skipped that one. I think 2 more cases. That one here is essentially this, also a rotating case. This is closer to, so to say, Earth's rotation, right? So the rotation, so to say, that is here, so to say, the surface of the Earth, and so the Earth is rotating around it. You get very strange behavior here. So some additional flow velocity are induced when you do the rotation. The mass flux changes quite a bit, so you have a mass flux in this direction because you have a pressure gradient. But this Coriolis force induced flow here, and if you start increasing the rotation rate, the mass flux in this direction gets smaller and smaller, so the velocities are getting smaller. While in the cross-stream direction, it starts to increase, rises to a maximum, gets smaller. You can find some rather complex formulas for that. That is done by a former PhD student. And we can again compare that to this large-scale DNS that were done also in our group. And we see exactly this. So this is the mean velocity in the streamwise direction. This is the cross flow. But if you increase the rotation rate, all of a sudden this one here gets much smaller and this becomes much higher. All that is essentially represented by this type of formula, which are solutions of this multi-point equation. One last thing that we found very recently, maybe, and we actually did some type of flow prediction thanks to PFG. That was the last couple of years one of the most successful projects. The symmetry theory suggested us that if we do this type of blowing and suction, the symmetry told us there should be some kind of a log behavior here in the center of this flow. The log, we talk to people from turbulence, the log usually are known only in the UO region. And we found from the symmetry theory, we should get some type of a log, but that should be valid, so to say, in the core region. Submitted proposal to DFG, was granted from the good PhD student. He did this large-scale simulations, and this is exactly what he finds. So the solid line here is log, and again, so this is log scaling, linear scaling, and we do see very long ranges of the log law here, essentially induced by this blowing and suctions, which in fact who are more closer to aviation, is of course something that engineers have been thinking about for decades, because blowing and suction can manipulate near-wall flows, and eventually we know that it can eventually reduce drag drastically, but technically it has not been implemented so far, but principally it's possible. So blowing and suction and this kind of behavior is important to understand. We can also compute all the other stresses and higher order things which are important. Let me say a few words on turbulence modeling. If you look at the history of engineering turbulence models, what will we find? So going back to the age of the 30s and even the 20s, very early turbulence models, for example, the one by Karman and Hunter, did not have all the symmetries of Euler values. That means they're outside of the cast. You cannot use them to design an airplane. It just doesn't work. With the development in the 70s of two equation model, KF, the model K omega model, these are these turbulence models you can find in any commercial code to design airplanes. And also with random stress transfer model, all symmetries of Navier-Stokes of Euler equation were properly observed. So only in the 70s, now we had a machinery, and at the same time, the new computers came, we were in a position to do flow prediction, but not very accurate. In particular, we do know nowadays, the KFs and the Kaman model, they have additions, unphysical symmetries. We look at this equation, and we find they have symmetries which are completely unphysical. So we have to be careful. We have to have all symmetries of Euler and Navier-Stokes. That's the basis. We need the statistical symmetries, but we should not have more symmetries which are unphysical. And leads to rather unphysical results, in particular for complex flows. So, for example, if you have large flex systems, you have recirculation zones, they are not properly accounted for. Take some of these very simple. From statistical symmetries, so this was, so to say, only Navier-Stokes and Euler. So now we have all the models that have at least, so to say, the minimum requirement. From this new statistical symmetries, this year is essentially captured by all models. That is surprising. So even early models have this type of statistical symmetry. So turbulence modelers implicitly recognize the importance of symmetries. Look at the development of turbulence models. Every stage of models were better in terms of symmetries. But you will probably never find any paper where they talk about symmetries. So we should and we will use symmetry to explicitly for designing new engineering turbulence models. So that is, so to say, the key message, and that is because we believe this is the heart of turbulence and the physics of turbulence that should be implemented. So let me come to the conclusions here. I'm not too bad at time here. So new sets of symmetries beyond what we have in Navier-Stokes have been derived from this infinite set of multiple equations. Turbulence not only restores but also creates some of these new symmetries. Very often you hear when you go to turbulence conferences, you hear people say, have long enough flow and then it becomes turbulence, so it loses symmetry, but then in a statistical sense it is recovered. But if you ask them, they never say what do they mean with symmetry. Usually they mean symmetries like reflectional symmetries or something like that. So turbulence creates symmetries very nicely. The key ingredients for classic and new scaling laws, so for wall turbulence, rotating turbulence, and many things that we can show, they're really crucial to understand that. Most important scaling laws for higher moments, I showed you the stresses there, the Rayner stresses. One key message to take home is these scaling laws, so to say, our ability to, so to say, to mimic the behavior of turbines, which were done by Navier-Stokes on thousands of computer hours and supercomputers. The scaling laws, they are solutions of an equation. That is something important. If you look at textbooks, the scaling behaviors are more type of curve fitting. They never solve solutions. They never solve equations. Symmetry should be part of turbines models, and I just a time ago I hired a new student. But there's a couple of open questions. So, do we have all the statistical symmetries? Is this complete? I just mentioned it very briefly. In the scaling laws, there are numbers, and in particular in this log law, which you find in any book, there is this kappa. If you do measurements, it's always, no matter where you do measurements, it's always around 0.4. Nobody knows where that will come from. That is an open question. And then there is, of course, we do see the symmetry-based solutions we derive are only valid in certain regions. It's not uncommon in turbulence, but the question is how do these different scaling behavior, how are they related? Reynolds number dependent is something very important for engineers, airplane engineers. In wind tunnels, you usually cannot reach the Reynolds number, the flight Reynolds number. So for a big airliner, the flight Reynolds number is something of the order 10 to the 9. In wind tunnels, we can never achieve that. So we would like to understand what is the Reynolds number dependency of the drag. Measure it maybe in the wind tunnel and have a theory to extrapolate this, what it means for designing an airplane. Well, I think I stop here. Thanks a lot.
Thank you very much for keeping us in time. We won 10 minutes in the last 35 minutes because we cut it short in the end, but the floor is open for questions before we break for lunch.
You just told us that the Reynolds number dependence is one of the open questions, which would be very interesting for engineers. But I have to see how you could introduce it into your model, because in principle it's not part of your statistical system.
Implicitly it is, actually. Implicitly it is. Let me go to a couple of equations. Here, I didn't, yeah, sorry, I didn't do that. This here, viscosity, if you non-dimensionalize the system, then it's one of the Reynolds. So always where you have viscosity here in the equations, when you non-dimensionalize, you always get one over Reynolds. The same thing, of course, because this equation comes from Navier-Stokes. Here we have Navier-Stokes, it also 1 over Reynolds is not equal. But this is a very, very difficult problem. We have a couple of ideas how to treat that, but it's not so simple in terms of symmetries here. But eventually, I think we can.
I really understand that you apply this model only for development flow. So you don't try to predict flight position.
No, I understand your question. We're not looking at transition. In fact, here I don't talk about transition. So we believe, true for most of the flows around the airplane, except for the nose region, the flow is turbulent. But so we only talk about turbulence here. But in fact, we just published one paper and one as a recent review. The idea of symmetries can also be applied to the question of transition. And one gets some very interesting new stability modes. Just too much for this one talk, but it's possible.
Are you planning to apply these new theories also to practical design problems? and validate it with experimental data?
Yeah, the first step is essentially, now that I believe we have a much deeper knowledge based on the symmetry, the next step in the next, say, 3 or 4 years, we will develop a new turbulence model that, so to say, is able to recover all the symmetry properties. And then the next step, so to say, sorry to say, but it will be maybe 5, 6 years or so. Yeah, we will definitely. We will use this turbulence model, this new symmetry-based turbulence models, as I would call it, to apply to practical problems. Yeah, definitely. That is the ultimate goal, definitely.
I got a little bit stupid question, but how just regular CFD engineer should choose turbulent model? Because I saw many works where people use different models and they get sometimes absolutely different numerical results. So how to choose the turbulent model correctly?
Right. Unfortunately, that is still a matter of experience. That's too bad. So there's not too much science in that. So you have to it's necessary that you have done many cases, tested many models. But I would say there is one rule of thumb. I'm not sure whether you're an airplane engineer or work in the area. As long as you have relatively simple shear flows, boundary layer type of flows, channel flows, so something that is similar to these canonical flows I showed you earlier. K epsilon, Q omega, the simple two equation models are not too bad, actually.
Okay.
As soon as you go to complex flows, say the flap system of an airplane on the airfoil, this will not work at all. What usually works much better, but has serious other problems, is what we call the Renner stress transport models. Another reason Modi wrote the Speciale Sakar-Gatsky models. They have serious numerical problems. LES, sometimes people think LES is an option. LES is not doable for engineering design purposes every day. I mean, if you as an engineer, your boss say, hey, this is a new wing, just do it. I would like to see the result tomorrow. LES is not an option. It will take you a couple of weeks to get an LES run for a wing. So we have to stick with these turbulent statistical models. But if you do complex models, complex geometry, Renner stress transport, but they are difficult numerically. Very often, if you can choose it, all the CFD tools have it, but if you start it, it will crash. You have a serious problem with stability. It will just diverge the solution numerically. A very good compromise is what I think is, it's kind of a blend between these two equation models and the Renner stress models. That is what they call the nonlinear two equation models, or explicit algebraic Renner stress models. They are kind of similar. They have a lot of physics from the Renner stress transport models and are still as simple as two equation models. They are stable, they are robust, so for everyday purposes they are not too bad. And even for complex flows, they are doing a fairly good job. So that is what I usually, that is a message I usually, if engineers ask me, what do you think I should use? That is, I think, a very good compromise, in fact. In fact, you can show, I didn't talk about that, you can show it has the nice symmetries we have to have from Euler and Navier-Stokes, fundamental mechanics. But they, so to say, they recover some of the properties from Renner stress transport models. Remember, I told you that the K-epsilon type of models, they have too many symmetries, unphysical. With these nonlinear or algebraic stress models, this unphysical symmetry is out. That is the main reason why it works much better. So you can always find a symmetry argument why one should use this.
Okay, thank you.
Maybe one answer.